Control systems. Control systems are an important part in technological advancement of humanity. To elaborate, a sort of control system is used in almost every structure in human history. For example, simple machines such as a bathroom toilet tank to more complex machines like a flying drone. Fundamentally, a control system is a combination of mechanical and electrical mechanisms that operate simultaneously to provide the desired output. In this video, we will evaluate two situations that revolve around control systems.
Question 1. Boeing 737 MAX control system. Objective 1. Determine the root cause for the airline disaster. Objective 2. Design a control system based on the maneuvering characteristic augmentation system MCS during takeoff stage. Objective 3. Evaluate design control system. History of Boeing 737. August 2011. Launch of 737 MAX. May 2017. 737 MAX started service. 29 October 2018. First crash of Boeing 737 with Lion Air with 189 fatalities. March 10, 2019. European Airlines crash with 157 fatalities. March 13, 2019. FAA grounded all Boeing 737 MAX. June 26, 2019. FAA uncovered data that caused the plane to crash. December 17, 2019. Production of 737 MAX has been suspended following by the resignation of the CEO on 23 December 2019. There's 4 root causes that causes a plane to crash: time, budget, design, and technical. For time, short deadline is given to complete against its competitor, Airbus. Budget. Due to the budget constraints, engineers reuse old plane design and elongate it that matches the requirement. Design. Engine size and mounted height. It is bigger and higher than ideal. For technical, it's error of angle of attack sensor AOA.
In this section, the design methodology of constructing a control system based on the 737 MAX is presented. The first step to our methodology is to determine the goal and the purpose of the control system, followed by identifying the control variables and then identifying the device that can influence the process and change the process output. Next, we determined a model of the actuator, process, and sensor, and also defined the controller and actuating signals. Following this, we also identified the feedback elements. And finally, designing the block diagram based on the defined control system and reducing and optimizing the design block diagram. The goal of a control system is to design a system that can determine the error in the angle of attack of the Boeing 737 and prevent it from stalling by actuating several variables. Ultimately, our purpose is to design a control system that resembles the maneuvering characteristics augmentation system. Prior to analyzing the variables of a control system, let us take a look at the anatomy of the Boeing 737. The main focus of this anatomy would be the angle of airflow sensor, the elevator, the rudder, and the engine intake. These components are mentioned in the next slide. There are 4 main control variables of our design system, which are the angle of attack, the airspeed, the yaw, and the aircraft fuel injection system. Our control system will be based off these 4 variables, and the definition of each variable is presented in this table here, as well as the components and its desired output. Under the components section, it is observed that there are 3 main elements to a control system, which are the controller, actuator, and feedback element or sensor. The controller adjusts the actuator in response to the measurement, and the actuator manipulates and causes an action, and the sensor or feedback element measures that response.
So what exactly is an angle of attack? Angle of attack is the angle formed between the wing chord line and the direction of the air flowing past the wing. At any specific AOA, the airflow over some percentage of the wing surface will generate lift as well as some amount of drag. Maximum lift is usually obtained at a relative high angle. The AOA system is a reliable measurement and the display of angle of attack from takeoff to landing can substantially improve aircraft performances as well as assure a safer operating margin for both stall speed. So this is our design control system for the AOA system. The input for this system will be the desired angle of attack. First, the maneuvering characteristics augmentation system (MCAS) will control the elevator and horizontal stabilizer. If the angle of attack is off balance, the AOA sensor will detect and send the data back to the MCAS controller to adjust the elevator and the horizontal stabilizer. Next, the flight control wheel is the controller that take controls for the rudder. The rudder is for the aeroplane to fly in a specific direction. When the direction of the aeroplane is not in the desired direction, the directional gyroscope will send a signal to the flight control wheel to adjust the rudder. So moving on, the mixture controls the fuel injector, which was responsible to supply the necessary amount of fuel to the engine for combustion in an aircraft. So during the high altitudes, the air pressure and the oxygen level declines, so the fuel tank mixture sensor sends the data to the mixture control and more fuel of the engine is combusted. And lastly, the throttle level, most often referred as a thrust level, is a controller which pilot controls the jet engine intake to ensure smooth airflow into the engine despite air approaching the inlet from directions other than straight ahead. If there is a disturbance due to the air turbulence, the tachometer, which shows the number of revolutions per minute, sends the data to the starting from the MCA, and the whole process is repeated. So this is the symbol of variables for our system. So when you simplify the block diagram, as you can see on the step 1, this is the simplified diagram, and since on top of them they are in series, you can times it together and you'll get this value. And then in the end, it's a negative feedback loop, so you get this value. Yeah.
Control system working principle. Working principle mainly consists of 4 main elements: input, controller, actuator, and feedback element. For input, the input or reference point supplies signals of the control variables. The variables such as angle of attack, yawning angle, fuel injections, and airspeed of the aircraft sends the signals to the summing junction and calculates the magnitude of error signals when compared to the set point. Next, controller. The controller sends an actuating signal, which is done by maintaining the value of the controlled variables at the set point. The MCS, flight control wheel, mixture control, and throttle levers send signals to their respective actuators to produce a response that corrects the error signal. Actuator. The actuator is the electrochemical part of the system which helps to achieve physical movement by converting the electrical energy into mechanical energy. The elevator and horizontal stabilizers corrects the AOA. The rudder corrects the yawning angle. The fuel injector injects fuel at the desired mass flow rate. The jet engine's intake produces thrust accordingly. Feedback element. An electrical signal is sent to the sensors from the output of the controllers to calculate the deviation from the required value. The AOA sensors, directional gyroscope, fuel tank mixture sensor, and tachometer ensures detects how much the value is different from the desired value.
Next, we move on to question 2 of the assignment, and the theme of this part is survival control system. We are provided with 3 scenarios. The first one goes by: assume you are trapped at a remote location and need to survive for at least 1 week. The site is surrounded by forest but close to a stream of river. And the third situation we have is a single airdrop of supply of instrument for a control system is dispatched. The main objective we have to figure out is to design a control system that can utilize the resource of surrounding. The next one we have Instrumentation and components to build the control system are in airdrop and it is dispatched. These are the two primary objectives we have in order to survive in the given situation before a rescue team appears.
There are certain issues that we need to take into consideration when on survival mode. This includes water quality, predators, shelter, medicine, inadequate sleep, and food supply. The primary issue on survival mode are poor water quality. Up to 60% of the human adult body is water, and it is estimated that a human can survive 3 days without consuming water. Therefore, clean water is extremely crucial to the human body, as they serve purpose to carry out many essential functions, such as balancing internal temperature and keep cell alive.
Right now, I'm going to talk about the design methodology for the water quality control system. So first, we identify the primary issue to human survival, which is the need of water. Then, we determine the control variables and obtain devices that can control and achieve the desired output. Next, a model of the controller, actuator, feedback element, and process was determined, and a block of diagram based on the defined control system was designed. And lastly, we evaluate and optimize the design block diagram of the control system. So the control variables for our water quality control system will be the turbidity of water, the pH value, and the water quality.
Let's take a look at the water quality control system that we have designed. As observed starting from the left hand side, the reference or set point is the desired water quality, which is the input of this system. The first element is a water pump, which is the process. The water pump receives water from the nearby river and moves the water through the pipes. This sends a signal to the summing junction just before the controller. The summing junction sends an error signal to the turbidity controller, and the controller sends an actuating signal to the chemical flocculant injector. The injector acts as an actuator that converts the electrical energy from the signal to chemical energy, where the water is mixed with the chemical to reduce turbidity. This then produces an output signal and approaches the first branch, where the turbidity sensor acts as a feedback element and measures the current turbidity level to ensure it meets its desired output before proceeding to the next summing junction. Next, the relay controller, which receives an error signal from the second summing junction, and the controller maintains the desired pH value of water. The relay controller switch then sends an actuating signal to the chemical injection pump, where it acts as the actuator and manipulates the pH level of the water accordingly. This then proceeds to the second branch, where the pH meter will detect and calculate the magnitude of the difference of the actual value to the desired value of pH levels of the water. Finally, the signal proceeds to the water pump and then to the water quality meter, where it detects if the water quality in terms of its pH value, turbidity, hardness, DO levels, and chloride levels are within safe levels before proceeding to the output, which is the actual water quality. And this system is known as a closed feedback loop. And the next step we took is to convert the variables into symbols for easy reducing and optimization. And this brings us to the next section, which is the block diagram reduction for our water quality control system. The main objective of simplifying the block diagram is to reduce the multiple blocks into one single block. Therefore, in step 1, the inner branches were reduced, hence blocks G2, G3 and H1 were combined, as well as blocks G4, G5 and H2. In the second step, it is observed that the first and second branch is combined to the two G1 blocks and produce a single block. The outer branch containing H3 is also combined to the reduced block diagram in step 1. So this leaves us with the reduced block diagram as shown in step 3. Step 4 then combines the two block diagrams in step 3 to a single block diagram in step 4. This is the simplest form of the block diagram that we have designed. And here we see the reduced block diagram and the transfer function of the block diagram.
Working principle for question 2 mainly consists of 4 main elements: process, controller, actuators, and feedback elements. Water pump moves water from the river streams to the water control system. Second, water pump is subjected to pump water from the turbidity control system to the pH control system. For controller, the controller maintains the value of the variable at set point. PID turbidity controller and relay controller switch sends actuating signals to the chemical fluctuant injector and chemical injection pump. For actuator, the chemical fluctuant injector and injection pump injects chemical into the mixtures to filter the water. An increase in carbon dioxide concentration will lower pH value and vice versa. Chemical reagent is dosed into the water streams to increase the effectiveness of settling or filtration process. Lastly, for feedback elements, the turbidity sensors is used to ensure that water is at safe levels of turbidity which is less than 0.3 NTU. The pH meter ensures that pH value is in the range of 6.5 to 8.5. The water quality meters ensures that the DO level, chlorine level, and hardness level are at the correct value and safe to process to the water tank.